Hi everyone, today I'm going to share question 4 of revision exercise 2.1 on applications of Newton's laws. So I have taken a screenshot of the scenario that student A and student B, they are connected by a rope that is taut. So in fact all of you would be able to get part A done correctly, the free body diagram of student A and student B. So I will not discuss much about this. This is student A, and the forces acting on student A will be weight. There is a normal contact force, and there is a tension force caused by the rope. I'm sketching this. I'm not sketching a full free body diagram. I did not put in the subscripts, and I did not put in the legend. So make sure you, when you are doing this question, put in the appropriate labels, legends and subscripts. Now for student B, the same thing goes. There should be weight of B. Let me be careful with my notation, weight of A and weight of B, and there should be also a tension force. Now for part B, the question wants us to find out what is the value of this normal contact force. Therefore, to find out the value of the normal contact force, we need to know what is happening to the two students. It's given in the question that the two students are stationary. A is stationary on the floor, B is suspended in the air. So we can say that the system is in equilibrium. Alright, so on student B, when we want to find the net force on student B, looking at the free body diagram, we see that the net force is simply tension plus weight. Let's define outwards as positive. The net force on system B must be 0 because the object is in equilibrium, so there's no net force, and therefore tension force is simply equals to negative weight. And weight of B is 60 kg times a negative 9.81. Do not forget the negative sign. The value of G is negative because gravity pulls things downwards, and we have defined outwards as positive. So if we solve this, we will get a tension force of 588.6 newtons. Positive force means it's pointing outwards. It verifies and tallies with our direction of tension force over here. Let's proceed on to student A. So on student A, we apply the same equation by Newton's second law. The net force on student A must be 0. And looking at the FBD of student A, this is simply N plus T plus weight of student A. So let's plug in all the numbers. 0 equals to N, which is what we need to find. Now tension, we realize that student A and student B are connected by one single rope, and the tension force in that one single rope must be the same throughout the rope. I mean, if there is some parts of the rope with higher tension, then the rope will tend to snap or break. We don't see that happening, so therefore the tension force in the rope is the same. So I can now put tension force as what I found previously to be 588.6 newtons, and the weight of student A, which is a 70 kilogram student with downwards G value of negative 9.81. If we solve this, we should be able to get a normal contact force of 98.1 newton, which is the final answer to part B. Double check that the force is positive and it tallies with our direction of normal contact force, which is pointing outwards. Alright, let's move on to part C. So in part C, it's given that student B is now climbing up the rope at a constant acceleration of 0.25 meters per second squared. So calculate the tension in the rope. So we are looking at student B. Let's look at the free body diagram for student B. Let's figure out the net force on student B. By Newton's second law, the net force on student B, I'm going to just use short form here. Newton's second law, make sure you write the full words. The net force on student B is equals to the mass of student B times the acceleration of student B. So looking at the free body diagram, there are two forces acting on student B, so I will just write this as per usual, equals to MA. And now let's make T the subject. T equals to MA minus away WB. So let's start to plug in the values. The mass of student B is 60 kg. The acceleration of student B is 0.25 upwards, so I should write a positive 0.25. And I minus away the weight of student B. The weight of student B is the mass of student B, 60 kg, multiplied by a downwards gravitational pull of 9.81. This downwards gravitational pull again has a negative sign. So if we solve this, we should be able to get 603.6 newtons, and I should round it off to two significant figures, which is 600 Newton. And that's the answer to C. Now for part D, the question asks when student B is accelerating upwards, like in part C, will student A be put upwards off the ground? Because student B is accelerating and climbing upwards on the rope. To solve this question, we need to look at student A, because that is what the question is asking about. Is student A being put upwards off the ground? On the FBD for student A, we can see weight, we can see normal contact force, and we can see tension force. Now, the tension force as calculated in part C is 600 newtons. The weight of student A, WA, of 70 kg and multiplied by 9.81, that should give me 686.7 newtons. So from these two values, you can see that the tension force acting on student A is smaller than the weight of student A. So therefore, the answer is no. The tension force acting on student A is smaller in magnitude compared to the weight of student A, and therefore student A cannot be put upwards off the floor. For part E, with what minimum acceleration must student B climb the rope to lift student A upwards off the floor? When the question says that student A is lifted upwards off the floor, we need to recognize that on student A, this means normal contact force is 0. The floor is no longer supporting student A. So essentially on A, you only have tension force, which was drawn wrongly. Should start from here, tension force, and also the weight of student A. And these are the only two forces acting on student A when student A is lifted upwards off the floor. So in order for A to be put upwards, we need the acceleration in this upwards direction. This means that my tension force, the magnitude of this must be much more than the weight of the student A, which is pulling student A down. This means that the tension force needs to be more than 686.7 newtons. So now back to student B. The question asks you what is the acceleration that student B must climb. So we need to look at student B. I'm going to redo and repeat this part of the workings, which is on student B. By Newton's second law, the net force is equals to mass times acceleration. Net force on student B is caused by tension force and the weight of student B. I need to rearrange the equation though to this. I'll have the whole chunk of the similar working here, and then I need to rearrange the equation to make acceleration the subject because that's what I want to find out, and therefore this is equals to tension plus weight of B divided by the mass of student B. Be very careful again in plugging in the numbers. The tension force is upwards force on student B, so that will be 686.7 Newton. The weight of student B again is 60 kilogram multiplied by negative 9.81 meter per second squared divided by the mass of student B, which is 60 kilogram. So if you do this properly, you should be able to get an acceleration value of 1.6 meter per second squared, which should be the final answer. So this 1.6 meter per second square is the minimum acceleration needed before student A can be lifted up. If we just if student B just climb with an acceleration of exactly 1.6 meter per second square, then the whole system will be in equilibrium and student A will not be able to be put outwards off the ground. The acceleration for student B needs to be more than this minimum value of 1.6 meter per second squared. And that is the complete solution for question 4 in revision exercise 2.1.